Okay, we're gonna begin this lesson with a very simple true/false statement. Okay, here it is. I want you to think about it before you answer. Do not say anything out loud. Just write down your answer, what you think it might be, and we'll go from there. Okay, there is the statement. I want you to say true or false. Just write down. Don't say anything to anybody else. I want you to just think about it on your own for 30 seconds. Okay, now that we have thought about it for about 30 seconds or so, I want you to justify your answer somehow in any way, shape, or form that you think is an acceptable way to justify whether or not you think it's true or whether or not you think it's false. Okay, let's have a polite conversation here. Put your hands up if you're voting for true. This is true. Let the record show no one's hands are out. Put your hands up if you're voting for false. Let the record show most people have their hands up as false. Okay, let me ask you an honest question. How many of you, even just for a little tiny bit, were a little bit unsure of whether or not this was true or false? Let the record show there's at least 5 people up in the room. Yes, here's why, right? Because this is so seemingly, well, this is true, right? Well, yeah, that's true. So why wouldn't this be true, right? Because it's a what? Right. It seems like it is. It should be true, right? Okay. How did you justify? Yeah, Matthew. What'd you do, buddy?
So I put the square root of
What?
4.
4. What'd you do?
So you'd be like, so if you say that's true, then that would mean the square root of 4 plus the square root of 9 equals the square root of 13. But we know the square root of 4 is 2, and the square root of 9 is 3.
Oh, I see.
And that would be 5.
Oh, I see. So you said the square root of 4 plus the square root of 9 would have to imply the square root of 13 if this was true, right? So you're basically doing you're doing a proof kind of like by a counterexample, right? So if we assume that this statement is true, then it must be true that this statement is true, but we know that this is the number, this is 2 and 3, this is the number 5, which is false, so that means that this must be false. I like that justification, very good. Did anybody do it differently? What'd you do? So a similar argument. Did anyone use their calculator? Nick, what'd you do, buddy? Yeah, okay, so the square root of 2 is approximately 1.41. The square root of 3 is approximately 1.73. And the square root of 5 is approximately 2.236. If you add this up, it definitely does not equal that. That's another justification. Is that similar to what you did, Nick? About? Yeah. Okay, good. All right, trick for you. We are going to move on to, I have box number 1.5. Box 1.5, okay? All right. This is box 1.5. How many of you have heard this term before? Like terms. Hands up if you've heard the term like terms. Good. You need 2 things in order for terms to be considered like terms. What are the 2 things that you need to have like terms? Yes, Decky. Same number. Can you be more specific? You need the same variable. Very good. Well, I mean, yeah, I'm gonna choose that different. Anybody know different though? There's something else I want for like terms. No, like terms. I'll give you one. You need the same exponent. You need the same exponent and the same, I think, what you meant by variable.
It's the number before.
You need the same base. Yeah, that's what that means, okay? So in order for it to have like terms, you need the same exponent and the same base, right? Because I could have like 3x squared and I could have 5x squared, right? So those are like terms. I have 3x squareds over here, I have 5x squareds over there, so altogether I have how many? I have a grand total of 8x squareds. This is the same exponent and the same base. So altogether collectively I have 8x squareds. You guys okay with that part? Yes or no? Let me know. Yes, we're good. Okay. You've heard of like terms. Have you ever heard of like radicals? Some of you have, some of you haven't. Again, just like terms, you need 2 things. You need the same, instead of an exponent, what do you think you need? Well, not sign. You need the same index. Very good, guys. You need the same index, and you also need the same what? Very good. Radicand. I love these words that you guys are using. That's absolutely correct. same index and same radicand. So for an example, I could have the fifth root of AB, and I could have 7 fifth roots of AB. So collectively, if I wanted to add these, how many fifth roots of AB would I have? I would have 8 fifth roots of AB, and this is where we're going today. Does this make sense? So I wanted to point out to you the fact that like radicals are very similar to like terms. You need two things, same index, same radicand. So you need the same index to be true, and you need the same radicand or the stuff underneath the radical to be true. Okay, let's talk about sum and difference properties for binomial radical expressions. So, for example, if I have a nth roots of x and I want to add that to b nth roots of x, well, first of all, are these like radicals? Yes, they have the same index of n, and they have the same radicand of x. Is that true? You guys go with that part? So therefore, the way that we would add this is we would take, well, that's just a plus b nth roots of x. And that's what we need to show, right? It's basically the distributive property because we have like radicals. So how do you think it works for the difference? Well, it works the exact same way. If I have the a nth roots of x and I want to subtract b nth roots of x, it is equal to a minus b nth roots of x, okay? So the thing that we want to keep in mind is that if our indexes are the same, we're good. If our radicands are the same, we are good. So we can take use of structure of the way that the binomials are set up, and that's where we're going today. You guys okay with this so far? Okay, let's do examples together. This first one here. I have a cube root of 5x minus 2 cube roots of 5x. First of all, are these like radicals, yes or no? Yes. How do you know? You need two things to determine it. Same, not same base, no. Same radicand and same index. Okay, so we can keep going. So this is going to be 1 minus 2 cube roots of 5x. And yes, you have to write it just like that. That's showing the math, right? That shows me that you understand the property and you understand the distributive property as well. So therefore I have negative cube roots of 5x, and this would be the answer. You guys good with that part? Everything right here would be the answer for us. So we have the problem over here, we have the answer over here, and we have the math in the middle. Okay? So yes, you got to show it all. Okay, here we go. Let's do example B. 6x squared root of 7 plus 4x squared root of 5. How do we add these together? We can't. Very good. You did not fall for it. Awesome. This is just 6x squared root of 7 plus 4x squared root of 5. These are not the same radicand, right? 7 and 5 are definitely not the same. Okay, let's make use of structure on this one. So what I mean by that is let's take a look at the indexes. Well, they are 3, right? So that's good. I'm good to go. And then here, my radicand, whatever it is, it's the same, right? So I don't have to worry about it. I know I can go over here. I'm going to go, this is going to be 12 minus 8 times the cube root of 7xy. So altogether, what do I have here? Yep, I have 4 cube roots of 7xy. Okay, I have 3 problems here for you guys to try on your own, A, B, and C. Show me all the math, get the answer, talk to someone sitting next to you, see what they got, check in with their work, and we'll come back together in just a minute. Okay, so part A is already simplified. You can't go any further because they have different radicands. Part B, I got 7x square root of xy, and then for part C, you should probably have 17 minus 15 fifth roots of 3x squared, so that's 2 fifth roots of 3x squared. Okay, ladies and gentlemen, the last 2 boxes of the day, we're going to be talking about how to multiply binomials with square roots, okay? If you're a FOIL person, you go ahead and set the FOIL. I'm a boxer, so I'm going to go ahead and set up my box, okay? I want 4 plus 2 rad 2, and I'm going to multiply that with 5 and 4 rad 2. Okay, if you like FOIL, go ahead and be FOIL, okay? Whoa, whoa. I love the box method, man. Alright, ladies and gentlemen, here we go. I'm going to do 5 times 4, that's going to give me 20. I'm going to go 5 times 2, rad 2 is going to be a 10, radical 2. Let's go with that part, okay? 4 times 4 rad 2 is going to be 16, radical 2's. Okay, now, how do you do 4 rad 2 times 4 rad 2? Decky, what do you think?
The rads cancel out.
Yes, the rads cancel out. Well, what's 4 times 2? 8.
Oh, I know.
And then the rads cancel out. So I just have left 8 times 2. So the answer is going to be what? 16. Okay? Yeah, that'd be 16 there. Okay, good. So then I'm going to combine all my like radicals and my like terms. 20 and 16, those are like terms. How much is that? That's 30. Okay, where did we get 16? Never mind. Okay, I have a 16 radical 2 plus a 10 radical 2. So this is going to be plus, this is going to be 16 plus 10 radical 2's. So I'm getting a grand total of 36 plus what? 26 radical 2's. Alright, 3 minus radical 7 multiplied by 5 plus radical 7. Okay, if you're a foiler, go ahead and foil. I'm a boxer, so I'm going to go ahead and set up my box, right? So 3 minus radical 7 multiplied by 5 plus radical 7. Here we go. Let's see here. Okay, this is going to be 15, yeah? This is a negative 5 radical 7. This is 3 radical 7's. And let's see here, this is negative 1 times 7, so just negative 7. Okay, good. 15 minus 7, how much is that? Well, yeah, 8, very good. Okay, 8. And then I'm going to have a plus. I'm going to have a negative 5 plus 3 radical 7.
Negative 2.
So I'm getting 8 minus 2 radical 7. You guys getting the same thing I am? Yeah? Alright, conjugates. We've seen this word before. What does this word mean, conjugates? What's it mean? Yeah, binomial conjugates, okay? So can you guys tell me what the conjugate of this would be if I say the square root of A plus the square root of B? What's the conjugate of that? The square root of A minus the square root of B. Okay, right now, could you guys please multiply that out, show me all the work, and put a boxer on your answer and check your work with your neighbor. And I'm a boxer anyways, yeah, I got it. So anyways, you guys should have come up with this, just the simple simplification of A minus B for conjugates, right? Okay, 2 examples in box number 6, here we go. Let's do this. If I do 5 minus radical 7, and I multiply that by 5 plus radical 7, this has the shape of conjugates, binomial conjugates, right? But notice what the formula says. It's talking about square root of each one. So this is going to be, I could rewrite this as the square root of 25 minus radical 7 times the square root of 25 plus radical 7. Okay? Look, everyone's all upset because they're not seeing what it actually says, right? A lot of people will just go and say, oh, well, this is just 5 minus 7, which is negative 2, and that's wrong.
Wait, doesn't the answer end up?
So, anyways, if you rewrite this as a radical, we can then take advantage of the rule that this is just 25 minus 7, so the correct answer then should just be 18, okay? Not negative 2, all right? All right, try this one and try to apply the rule, okay? 6 minus rad 12 times 6 plus rad 12. Try to apply what it says. Okay, do you guys come up and see that this is just 36 minus 12, which is just 24? You guys come up with that one?
Yeah.
Okay, there's a reason why we need this rule, and the reason that we need this rule is for box number 7, and it's all about dividing. Okay, this is why we need that conjugate space up above to understand what it feels. So, we're going to do 2 examples for dividing. We're going to do this. 3 radical 2 all divided by the square root of 5 minus the square root of 2. Alright? So you have to be thinking in terms of conjugates in order to simplify this expression. We do not want any radicals in the bottom, and we want all positive exponents if we happen to get there. So Elijah, what do you think, dude?
What's the difference between this and
Yes, exactly. So remember, we're allowed to do this because this is just a fancy 1, right? We're multiplying by a fancy 1, so we're allowed to make this whatever we want as long as it's a 1, so we're not breaking any rules. So the fancy 1 that we're going to choose to multiply by is the conjugate. Radical 5 plus radical 2, radical 5 plus radical 2. So now we can take advantage of the denominator as just being 5 minus 2. See how that works? Okay, then I have a 3 radical 2 on the top, with a radical 5 plus a radical 2 in the middle. So there's my intermediate step. And I'm taking advantage of the rule in the denominator. Okay, so now I'm going to have 3 radical 10s plus, what's 3 radical 2 times radical 2? It's the number 6. Yes, because it's 3 times 2. Oh, it's very good. Divided by 3. There we go. Does everyone see where the 6 comes from? Okay, the 6 comes from here. 3 radical 2 multiplied by radical 2 is 3 times radical 2, which is just 3 radical 4, which is just 3 times 2, which is 6. That's where it comes from. Alright, so now we're going to say that we can pull out a 3, right? So what will that leave us with? Radical 10 plus 2, yep, all divided by a 3. Now we can cancel, so we end up with the square root of 10 plus 2 for our final simplification process. Alright, here we go. Let's work this one out. 2 radical 7 multiply or divided by radical 3 minus radical 5. We're going to multiply by a fancy 1, right? A very fancy 1. We're allowed to do that as long as we keep it as a 1. So what should my fancy 1 look like? Radical 3 plus radical 5. Very good. Radical 3 plus radical 5. Good. What does that give us on the numerator? 2 rad 7 times a rad 3 plus rad 5. I'll get there in a second. You're right. On the bottom, what do I have? I have 3 minus 5. Very good. So look at what we're doing here, right? We're showing exactly what's going on in terms of each algebraic step. So the numerator, I'm going to have 2 radical 21, right? Plus 2 radical 35. And the denominator, I'm going to have a negative 2. You guys good with that part? All right. What's the greatest common factor of the numerator? 2. Yeah, pull a 2 out. So pull a 2 out. That leaves you with the square root of 21 plus the square root of 35, all divided by a negative 2. All right, negative 2 and the regular 2 simplify to, I'm getting negative 1 times square root of 21 plus, my thing just messed up. 21 plus square root of 35, which is the same thing as negative square root of 21 minus square root of 35. Either answer is totally acceptable, but this is the one that I would choose to put as my answer.